So today is a bit messy. We are going to start, because of that, reviewing some stuff that I'm going to say probably you're going to sit there and be a little bit like, this is so simplistic. And I promise that it takes a turn in the middle of the lesson where it becomes less simplistic. Okay, so I apologize for that. The idea of doing that is so that you can hopefully, as best as you can, start to make these connections to stuff that you already know. Okay? So here's the two situations we've essentially handled so far. We've handled sum of torques is equal to 0, and sum of torques is equal to I alpha. Which one of these equations, when do you deal with these equations? What might a person do to be dealing with these equations? What might it look like if I was going to do these?
When your object is not angularly accelerating, you would use the top line, but if it is, you use the bottom line.
Okay, so essentially this is like Newton's first and second law, right? Except it's actually called Newton's first and second law for rotation. And usually they just, as the same thing what we did with sum of forces, you usually start right here with the Newton's second law, and then if it is 0, great. Okay, so let's watch a video here real quick that goes hand in hand with this. I love that this video is entitled dumbideas.info. Okay. Pause. Nope. Pause. No, I don't want you to come here. We'll do that in a minute. Technology. Listen. Listen. You and I are going to come to blows. It's not. You're right. Here, I'll prove it. All right. So discuss in your group how that relates to these equations, that situation that you just watched. If you need it, I'll put it over here again, but let's put it on mute. And you discuss with the group, how does this situation relate to those two laws?
So if we look at it, if we put the axis of rotation is like straight, like how could you think about this? Okay, it's 0, until the very end, but it's over. But then if we look at it, we put it through the C poles, and then so there's 6 up to 8 to these. At the very beginning, there's no torque at all.
No, I put it on blue. Come on.
Yeah, so sum of torques equals 0.
Are we doing 3D torque out here?
Are
we doing 3D?
No. I mean, sort of. I'll talk about that actually a little bit today. No, but sort of.
It's probably not 3D torque, it's 2D torque, but you have to do it.
All right. So, which equation probably best suits this situation? Absolutely the second. How many forces are acting on the gentleman doing the idea that we're looking at here? 3. What are they?
Gravity,
Gravity, lower and yes, normal and leaf lower. Okay, is gravity going to cause torque? Why not? No, it's not. It's no lever arm, right? Gravity is at the center; they're rotating about the center. Okay, is normal going to cause torque? Because that's the parallel one. That's the one that it's not. Here's the center; it's applied down here. So there's a lever arm, but it's straight up along it. It's basically when you balance something, right? Like if I'm trying to balance this guy right here, obviously I'm not going to try to do that with my coffee. But what I'm going to try to do is keep my force normal underneath it and cause it to be parallel so that the gravity of this does not cause any torque and the coffee rotates out of me. All right, finally, what's the actual thing causing torque? And why does the leaf blower cause torque?
Because
It's got a lever arm and it's perpendicular. You can see that both from the video. In the setup, you can see that they bring this arm out over here, so it's pushing ways away, and he angles it so it stays at 90 degrees. So what do we get out of this? We get that since there's only one thing, only one force, there's only one torque, if you only have one torque, is there any possibility of getting this first situation? Nope, it has to angularly accelerate. Cool. All right, let's use that to make a little bit of a transfer here. But before we do that, we're going to take a brief trip down memory lane. As a matter of fact, let me give you the title of today. Today's title is Angular Momentum. So let's take a little bit of a trip down memory lane back to chapter 6 and chapter 4 to discuss some stuff in regular momentum so that we can kind of pull over here. For starters, okay, what was the equation for momentum? Now, I will tell you, because I just had this conversation in physics too, so this is a little bit of a head and a side, and so I apologize if this is not interest to you. Okay, that is actually not the best definition of momentum, because that momentum definition there implies that you have to have mass in order to have momentum, which is not true. There are objects that do not have mass that imply momentum, and I'll explain that here in just a second when we do this. Out of that, we began, I promise to explain further, okay? We started here. We went back to Newton's second law. And with Newton's second law, I said, what simple thing could we do to get momentum into Newton's second law? As a matter of fact, where is velocity inside Newton's second law? Acceleration. What's acceleration? Yeah, so we get mass times change in velocity over change in time is equal to sum of forces. And then right here, okay, that, well, come on, not what I wanted to do. All right, that guy right there is what? Close, not quite. That is not momentum, but you're very closer with that. Change in momentum, a very, very, very important distinction. And so you get this equation right here. Now, you might not be a little bit used to this equation, but if I just simply take a couple of these things, oops, no, not like that. No, hold on a second. That's not what I asked for. Okay, and just move them around. Do you recognize it now? That's the impulse momentum theorem. The impulse momentum theorem, as we said before, is really just an equation that is like a further extension of Newton's second. But some of you might have heard me say this, so I'll say it again. That was actually the equation that was used for Newton's second law by most physicists, and actually still is. That's the predominant equation that is used by physicists for Newton's second law. Why don't we do that here? Mostly because it's way easier to explain acceleration and then mass and then sum of forces to kind of a group of students that are trying to learn this for the first time. But this is actually a better equation. Why is it a better equation? Because what it implies is that momentum is not something that has mass. Momentum is something that when it changes for an object causes force. And this allows us to take objects that do not have mass, photons light, anyway, and they can actually cause force because they carry with them momentum. We can get into that when you get into like the later chapters of physics too. What it do?
So like changing momentum causes force?
No, it's backwards of that. Force is still the cause, but momentum is kind of this thing that you can change an object's momentum when and force causes that. Force causes the change in momentum. So another way to say that is a photon, which has no light, comes down and runs into like a piece of metal. Okay, it runs into a piece of metal and it gets absorbed, aka it changes its momentum. It's gone from some momentum to zero momentum. Okay, conservation of momentum says that momentum has to go somewhere. So what happens? It gets absorbed by electrons, and electrons get shot off, which do have mass, so you can apply a force because there was a force on the photon coming in to stop it, and now there has to be an equal and opposite force, Newton's third law, to the electron. It has mass. It doesn't have to have mass in order to have momentum. Don't worry too much about that unless you're into that type of thing. But it kind of separates momentum away from that particular equation right there. That is still the equation for objects that have mass, but not important right now. What is important is this. Okay, so we had three major equations in the momentum chapter, and they were as follows. One, here's my equation for momentum. This equation, the impulse momentum theorem, is how you changed an object's momentum. Okay, and then there was one more. What if you didn't change the object's momentum? Okay? If the total momentum didn't change, another way to say that is that the momentum is conserved, and we went to this equation over here. All the momentums at the beginning have to equal all the momentums at the end. Yes? Let's look at a very, very, very simple situation with that before we actually pull out and change things at all. I have Sally, and I have thrown her in the depths of space. I threw her earlier, so she is moving. What do you expect her to do? Keep going. And this is a very simple situation because conservation of momentum, how many momentums do we have in this situation right now? Just the one, right? So if we simply look at this equation, this is a dumb situation, Sveinauer, because if momentum's going to stay conserved, we know that velocity is going to stay the same. Why is velocity going to stay the same if momentum is conserved? Because what don't you expect to change? There's probably a reason I'm addressing this, but we'll get to here in just a minute. No, yeah, you don't. Now, here's an interesting thing. Let's play pretend. Okay, let's pretend that there was a ray gun or some magical sci-fi ability for me to point at this at Sally and change her mass on the spot. Not change the number of atoms, but somehow change how they affect her in some way. Let's say I could somehow reduce the amount of inertia that a bowling ball had. Okay, if momentum was conserved still, what would then have to happen as her inertia reduced? This number stays the same. That number decreases. What has to happen? She would have to go faster, which we don't expect to happen at all to Sally. Her inertia is not going to change, so her velocity is not going to change. Cool? All right. Here's what we're going to do to transition over to rotational. I'm going to kind of use a cheap trick, and it's this. I'm going to remind you of analogies real quick. Actually, I did the wrong one first. My apologies. So we did this conversation a few times. We'll do it a few times more. My apologies for that, but it's kind of helpful. Rotational equivalent of displacement. With angular displacement. Cool. Angular velocity. Nicely done. Somebody else. Look at you going. All right, somebody else. Torque. And finally, moment of inertia. Correct. Remind me real quick what a moment of inertia is.
The ability to stop angular.
Yeah, so the resistance to rotational motion in the same way that inertia is the resistance to linear motion. And how do we actually change that? Like, what could you look at in an object and see its moment of inertia?
Like a force.
Okay. Not quite, sorry. What could you do to an object to change its moment of inertia? Not necessarily spin it. You could change its mass, although that's probably less. So let's say you, right? Can you change your own moment of inertia, even though you're probably not going to change your mass right now? Yeah, like literally, look, what did I just do? My moment of inertia is now larger. It is harder to rotate me here than it is if I were to do that right there. Yes? All right. Now, let's take those analogies and these understandings of momentum and simply go, okay, if that is momentum, then what is our beginning equation for angular momentum? My apologies for this. Angular momentum is capital L. I don't know. You get to the higher physics and people are like, why is it that letter? Just get used to it. I'm sorry. I apologize. It is what it is. And we are now going to do a very similar thing. Yes, what's up?
Is moment of inertia like its replacement for mass in angular talk?
Mm-hmm. In replacement for its inertia, not its gravity. Yes?
What's the L?
Angular momentum. So if you'd like, that's the whole topic of today is this guy right here. All right. Continuing on with our analogies of what we did just a second ago, let's begin here. Instead of Newton's second, we begin at Newton's second for rotation. And if we wanted to get angular momentum into this guy over here, we see that I is already in both spots. Where would angular velocity be? If you just draw the analogies from earlier, this should be very easy to do. Inside the angular acceleration. What's the equation for angular acceleration? which I'm doing my best here to draw very simple analogies here. So, what's that there? What is that I put in pink there? That would be the change in. All right. This, if I move this over here, and you can do this whatever you want. We're talking a lot of concepts today. We're not worrying too much on the math. As a matter of fact, I don't know how much I'm going to expect you to do math with this equation. The only main reason I'm showing it right now is because I think it's very helpful conceptually for what I'm about to do next. But this is known as the rotational impulse momentum theorem. Okay? Now, over here, the impulse momentum theorem showed us this. Simply put, if you put a net force on an object, I'm sorry, let me just take a step back. If you put a net force on an object using this right here, you'd expect the object to accelerate, right? Cool. If you put a net force object here, you'd expect the object to increase its momentum. But if it increased its momentum, you're probably not going to expect that to change. So what are you probably more than likely expecting to change? Velocity. Simply put, yeah. They say the same thing. Now, we come over here. What does the impulse momentum theorem tell us? Very simply this. If I have a net torque on an object, what's going to happen? Angular momentum is going to change. So let's go back to the very first video and review it from that particular stance. Is there a net torque going to act on this guy like we talked about earlier? Yes. So, is his angular momentum going to change? 100%, very easily. In what way can we very simply see that his angular momentum is increasing throughout the video? Angular velocity is increasing is consistently throughout the particular process. By the by, a quick aside. Okay, we mentioned briefly kind of sum of torques in several directions. This is going to happen. It's going to happen today, so I want to talk about this. One thing you do have to be a little bit careful of in torque, and we're going to try to simplify this for the most part. Torque, technically, you know how forces happen on technically 3 axes, but we really only worry about 2 most of the time? Okay, if we could somehow usually work a way of not messing with the 3. Technically, torques also mess around with 3 axes, but we only usually worry about 1. Your 3 axes are, if it's spinning along the y-axis, it's rotating like that. That's somebody doing this, right? If it is spinning along the x-axis, I'm not going to be able to pull this off in front of you, but essentially, okay, that would be someone pulling off a cartwheel at that particular time, okay? If someone spins along this axis, this would like them spinning this way, like a forward flip, okay? Now, almost every single problem, what we deal with is we just look at one axis. Let's not worry about all of them at the same time. It's no big deal. One thing to point out in this particular case is that he does, in fact, have to deal with 2 axes, because right here, this axis is what he's originally spinning on. But because of spinning on that axis, what happens, and the reason he falls over, is that his gravity, let's represent him by this stick right here, okay? Eventually, because he's spinning further out, it's going further out in a circle, and eventually his gravity gets outside the ability for force normal to push up. So if instead of looking at it like the vertical axis, we instead look at the axis that's pointing out at us, is there going to be torque along that axis now? Yes. And so what does he do? Falls over, right? So he's trying to keep himself balanced so he can just focus right here, but eventually what happens is he starts focusing on this axis right over here, which will matter a little bit later. All right. And finally, that has no scientific value whatsoever. All right, next.
There's something about the element of risk and danger that excites a crowd. And this crowd here at SeaWorld looking up at Rick Charles, 24 years of age, are fascinated. Some of them giggle nervously, all of them looking straight up 172 feet.
Favorite thing about this video you're about
to see if Rick Charles can come down safely through the air and enter into the water. Knees very heavily taped.
Got a forward double somersault, half twist.
Ah,
This is the dive that Pat Sucre made.
There you go. There's 172.
This is his girlfriend, Linda. Look at the face. She's talking to herself nonstop, a couple little smiles, a couple nods of confidence. Look at Rick up there, eyes closed, meditating. What's it going to feel like? What do I have to do right off the top?
There, by the way.
And there's Linda praying for him down below.
Freaking out as he's like,
Never done this before. He does not know what to expect. He's in the air. He's in good shape. Very good. All right, he didn't hit well. Now, he could have hurt himself. The dive was good. It was solid. He's a strong competitor, strong diver, but he...
All right, here's what I want to focus on. His rotation. Let's begin with this, okay? At the beginning, as he's standing there on the platform, does he have angular momentum? Does he have a moment of inertia? Yes, so why doesn't he have angular momentum? Well, some of us are overcomplicating this. What simple thing can we look at to see if he has angular momentum? No angular velocity. He is not rotating at all right now, so there is no angular momentum. All right. Is it fair to say that when he fell, when he was actually that he had angular momentum? Was he rotating during that time? Okay. So I'd like you to discuss in your group is use this right here to discuss what happens to him, what do all divers do, what did he do to change his angular momentum? Discuss. 30 seconds a minute. We'll go over. Sure.
Yeah, but he's just saying body. The more he rotates,
Because he didn't have any, he wasn't rotating at the beginning.
All right, here he is at the very beginning, so you can see it again. What does he do to gain
Never done
angular
this before. Does
momentum?
not know what to expect.
All right, what does he do? He leans forward and
He makes his radius larger.
not quite. Nope. What does he do after he leans forward? Not before it's after this part. What's that? Pushes up. So why does he lean forward before he pushes up? So there's a lever arm. And now that there's a lever arm with that force up, what is there on him? Torque. And so while there is torque, he is going to change his angular momentum. Yes? But here's the deal. Once he's in the air, how many forces are acting on him? One. What is it? Where does it apply? At the center of mass. So somebody asked about this the other day. This is a great example of this. So since there's only one force, is he, let's talk equilibrium for a second. Is he in translational equilibrium? Nope, because he has sum of forces, and therefore he will angularly accelerate. However, based on the fact that that force of gravity is at the center of him, will it cause torque? So, if it's not going to cause torque, should his angular momentum change? No. But one thing you notice throughout that is he speeds up and slows down. Yes? So let's break that down. What happens if this doesn't change? Well, another way to say that it doesn't change, we could say, I'm going to move this around just a little bit so I have a little more space so I can put all these on the same screen. Another way of saying it doesn't change is I could say it's conserved. All the angular momentum at the beginning is equal to all the angular momentum at the end. Now that's a really complicated one. Let's add up all of them, but how many angular momentums do we have here? Just his, right? Just that he's the only thing rotating. So we would say angular momentum initial is equal to angular momentum final, right? Okay? And how do we calculate an angular momentum? Okay, so by the way, I want to point this out. I only came over here once I said it's no longer changing. And what is it that causes the change in angular momentum? Net torque. So let's put this on this qualifier. When am I going to use this? I'm going to use this when sum of torques is equal to 0. or angular momentum is not going to change. Now, I say all that to then say this. Watching this video, going back a little ways. When does he spin the fastest?
Form down below.
He's never done this before. He does not know what to expect. He's in the air. He's in good shape. Very good. Right.
When did he spin the fastest?
Now he could have...
Why? It's not because he's at the top, by the way. Why is he spinning the fastest up there? No, someone. So say that a little bit differently, but I'm going to repeat what AP just said. He brought his mass together, so what did he do? Backwards. By bringing mass closer together, in that case, at the top, he had his mass very close together, so his moment of inertia was small, so his angular his angular velocity had to be large. And what happens over here then, as he spreads himself out? Moment of inertia goes up. Okay, so what has to naturally happen if angular momentum is conserved? Trenton and I were having this conversation that I think some of you overheard the other day. There's this weird thing where you start to get into, like, wait a minute though, you said sum of torques is 0 gets into angular acceleration. Didn't his angular velocity just change? And the answer is yeah. So didn't he angularly accelerate with the sum of torques of 0? Yeah. So the better way to look at this is not sum of torques causes angular acceleration most of the time. It's that sum of torques causes a change in angular momentum. Can angular momentum stay constant and you change angular velocity? Yes, as long as this is the case. See, this is the backwards of why I brought up Sally earlier. Sally's floating in space. It's just the momentum of Sally initial is equal to the momentum of final. But do you expect the mass of Sally, it's dumb that I'm writing initial and final of Sally, do you expect this mass to change? No. So do you expect the velocity to change? No. Whereas in this case, if you get a person spinning in space, you start spinning them around, so they have a moment of inertia, they have an angular momentum in total because they have an angular velocity. If they pull their arms in, what's going to happen? Yeah, their velocity is going to increase. Let's demonstrate again. I know that we've done this demo before, but let's talk about it from all of this perspective. I need another volunteer. To kind of focus on these equations and how they all come together. Okay, we'll stand here and put your arms out if you would, please, Isaiah. I'm going to turn you towards everybody. I'm going to spin you for a while, so just as a heads up, okay? So notice very carefully how much angular momentum does he have? 0. What do I have to do to give him angular momentum? Well, be a little bit more specific, but you're right there.
Put a force on him that's perpendicular.
I have to apply a torque. Right, a force, so a lever on, like, if I just shove him in the center, do we expect him to rotate? Okay, well, not on that axis, maybe a different one. So I give him a torque. So this is the first equation. Now, is anything giving him a torque? No. So what do we expect to happen to his angular momentum? Should stay constant. We're over on the right side now. So I'm going to give you back. Now, we are assuming no friction. There is friction, by the way, causing a little bit of the opposite torque, which is why he'll eventually come to a stop. So let's assume no friction in this case. Okay? And so I asked him to pull his arms in. And what happens? Did his angular momentum change? No, because there's still no sum of torques on him. Push your arms back up. And yet his angular velocity changed because his moment of inertia changed in this particular case. All right, thank you, sir. Or not see it if you want. All right. So that's what we're dealing with here. Okay. Now we're going to look at a series of these examples, mostly non-numerically. This is going to bother some people. I'm not going to put numbers to this today. We will eventually put numbers to it. Okay. Just as a heads up, I think I said this earlier, but to reiterate, I'm not going to expect very much math in this equation whatsoever, albeit it is relatively simple, honestly, to plug and chug. It's just really just a sum of torques problem like you've been doing. Okay. This right over here is mostly where we're going to spend a bulk of our time numerically eventually. But let's look at some other circumstances to come up with. As a matter of fact, one of my favorites. You can do this yourself, actually. You take a group of people to the playground. You have somebody spin at the very beginning. What's the person spinning at the very beginning doing to the system? applying a torque to increase the angular momentum. But the moment they stop, is there any net torque on the system? No. So you play a game, and the game is called Who Can Get to the Middle,
One,
and Who's
two,
Screwed.
three. Come on, Chris, go in, Chris!
So the thing is, the reason why this happens is number one, let's start with the basics. Why do they speed up as people go to the middle? Moment of inertia is decreasing. So in order to conserve angular momentum, what has to happen? Their angular velocity has to increase. Now, why is it impossible for them to get back to the center? It goes all the way back to centripetal acceleration. If you'll remember, the faster they're going on the outside, the more force is required to be at that particular radius, right? So it increases the faster they go, and the faster they go, the harder and harder and harder it is to hold on. And that makes it even worse when you want to get to the center, because it's getting even faster as you get to the center, requiring even more force. So if the first person probably does a decent job and they can get there. Everybody else, yeah, you probably don't have enough force in your muscles to be able to pull it off. What's up?
So, I'm not, so it might not be the right question I'm asking, but, so, your angular momentum has to be conserved because, like in a situation like this case, you know we're supposed to have on it, or change something, whatever, the angular, like, the momentum has to be,
Angular momentum has to be. Yeah. If no net torque is acting on an object, angular momentum will be conserved. Okay. Let's put some context to this. Let's get a little bit of some ideas. Okay. There's some crazy things that can kind of come out of this. Okay. First of which, the Earth spinning towards the east. Okay. Has as long as I've known it anyway. Okay. And spins to the east, and it has a particular angular velocity such that it takes the Earth to go around in about 24 hours. All right. Now, let's say I decide, you know what? I don't like that. I don't like that the Earth takes 24 hours to go around. Okay? I'd like it to take less time. So I get on the ground. Okay? I get on the ground and I start spinning east. Technically, by me spinning east, I'm spinning east because I am pushing the Earth. I'm using the Earth to cause me to rotate this way. What's that doing to the Earth? Causing it to push the other way. So by rotating to the east, what do I technically do to the amount of time in a day? I decrease it.
Very slightly.
Yeah, and when we're talking slightly, I did some math on this a few years ago, just as a heads up. If the entire Earth's population, all 8 billion people, from their entire lifetime, spun in a circle, like they didn't eat, they didn't sleep, they just spun in circles for the sake of doing this, it would take about 10,000 years to reduce the time of the day by about 1 second. So, just a heads up, priorities as far as that's concerned. But, let's continue with it. Okay, let's do some other demos. I'm losing people here. Come on, I know it's not an easy subject, but you got this. All right, I need somebody else for another demo, please. Come on up, Kinsey. Now, we're going to try to do our best to explain this demo in the form of a conservation of angular momentum. Okay, you saw some crazy things the other day. Let's try to match it. All right, so I'm going to have you stand there. Come on. Okay, I'm going to have you hold this. I know you guys saw this already. Okay, but here's what I'm going to point out. What is Kenzie's angular momentum right now? 0. Okay, and the wheels is definitely 0. Now I'm going to spin it. Okay. Oops, sorry, my apologies. Well, so you can do that. Okay. I'm going to spin it. Now, does the wheel have angular momentum on this axis? Does it have any on the axis that she's on? No. So she has no angular momentum. It has no angular momentum. So in total, what are their angular momentum? 0. Okay, go ahead and do the thing we did the other day.
Change it now.
No, go ahead and keep that the same way. From the top down, we try to put it more like this. From a top view, which way is the wheel rotating? The clockwise or counterclockwise is what I'm looking for. From the top view, what is it? Clockwise. Which way is she spinning? Why? Why is she spinning the opposite way as the wheel? Well, some torque is 0 across this whole situation. I think you're in the right thing, you just said the wrong word. What has to be a total 0? Sorry, my apologies. I'll have you do another one in just a second, okay? I got you over here. Sorry. Oh, my apologies. No,
You're good,
okay, sure. Alright, so in total, what's our angular momentum and the wheel's angular momentum have to be? 0. So conservation happens when she spins it like this. What's the total have to be? 0. So in order for it to be 0, they have to spin in opposite directions. Which object, the wheel or a person, is going to be spinning faster?
The wheel.
Why?
Because it has less mass.
They're close, but not quite. You're right, you're wrong. Less moment of inertia, which probably is a result of less mass, but yes, it is less moment of inertia that happens. Now, the really interesting one is the other demo that we did. Go ahead and stand back up there, wheel, okay, in this particular case. And it's interesting because, take this, we start it off in this particular case, and of course, how much angular momentum does she have? 0. I'm going to go ahead and spin this, let's go counterclockwise. Okay, and go ahead and turn it all the way around.
Whoa, whoa, whoa.
You'll slow down eventually. All right, if you want to slow down, you can. It's not about this. Okay, so notice, which way is she spinning super fast? What was it originally spinning? Counterclockwise. So she had 0, it had counterclockwise, so in total, the angular momentum was counterclockwise. So what does that mean? The total has to be at the end. Counterclockwise. So when she flips it to go clockwise, what does she have to do to get back to 0? She's got to spin clockwise. But not only does she have to spin clockwise to get back to 0, like she did in the first example, she's got to spin even more clockwise because the total has to be clockwise. Does that make sense-ish? Yes.
So if you spin Kenzie, it would
Ooh,
just.
excellent. Ooh, I like this. I think I like where your head's at. Here, let's go back up. Ooh, this is good. This is good. Okay. I don't think I've thought of this before. This is better. Okay, start like this. Okay, start like this. Okay. I'm gonna start spinning you. Okay. Turn the wheel upside down.
Oh, it's spinning. That's so crazy.
The wheel's not spinning. Not very much. Okay.
Is it
Why is there not as much in this particular situation?
My moment of inertia is.
Person's moment of inertia is going to be much larger than that of this, so it's not going to be nearly as big of a switch in that particular case. But yeah, it should, in order to conserve angular momentum. Wait a minute, should that have switched it?
Well, because what I was.
Ooh, I got a better one. I got a better one. My apologies. I don't think my demo was good.
I'm just worried about that.
If the wheel was part of Kenzie's system, then if you pushed her, then the wheel.
So here we go.
The wheel not spin.
Here we go. Okay, I start spinning. Okay, and I'm gonna stop you, Kenzie. Okay, I'm gonna grab your bottom hand. Cool. Oh, goodness gracious!
Sorry.
Didn't do what I thought it should do. That's probably because we were a little bit off. Let's try again. Try again. I'm sorry.
You're fine. You're fine.
There it is. All right. Thank you. All right. I've not done that demo. I like that we had that one. All right. So let's do some situations back up here because the people online have been waiting for us to just look at stuff in real life and not look at them at all for a little bit. So let's look at some situations. Okay. How am I going to do this in the math? Well, for starters, let's begin with the wheel example. Actually, let's begin with like a person, Isaiah, by themselves. And I'm not going to do numbers, but I'm going to show you kind of what it is you're going to end up doing. It's going to be something like this. So you have a person like a skater that's way spread out, okay? And they've begun with an angular velocity, probably from some type of torque earlier. You begin here, and then you go, how many objects are rotating? Well, in this case, it's a single person. It's just one person. So it would be the angular momentum of the person initial is equal to the angular momentum of the person final. And each of those are going to be calculated as moment of inertia. And this is what we were talking about a minute ago, so I'm going to go quickly through it. So what happens if I take this number and I make it go, I don't know, I make it less. I'm going to make it like 3/4 of what it previously was. What will angular velocity have to do? Increase by how much? Why 4/3? Because the total has to remain exactly the same as what it was before. The Total can't change. It's conserved. All right, let's do another example, okay? This time, we've got the merry-go-round. And I'm a top-down view of the merry-go-round. Here's a kid sitting on the merry-go-round, okay? Now, we begin all of them going. Someone pushes earlier so that there's an angular velocity, okay? We start conservation of angular momentum. All right. And the first thing you're going to do, you're going to start here. You're going to say, how many objects do have an angular momentum? What object has an angular momentum in this example? The kid. All right, so the child. So let's go angular momentum of child initial. Anything else? Merry-go-round, correct. And I'm going to do that for both objects, the initial and the final. By the way, subscripts are going to be a pain in the butt when we finally do the math on this. Now, obviously, if they begin spinning, they have some angular velocity. Let's talk about this. Does the child have an angular momentum to begin with? Actually, let me help you out. Before we do this further, we need to do something we did in torque. We need to have a fulcrum. We need to have a center point of rotation. Where's the center point of rotation? Center. Sure, obviously, it's right there. So let's make that. Let's child. Okay. All right, so does the child have an angular momentum? Yeah. They got a moment of inertia. They have an angular velocity. Yes? Does the merry-go-round have an angular momentum? Yes. It has a moment of inertia. It has an angular velocity. If the child doesn't move, what very simple thing do we expect to happen? Keep rotating the same way as before. But let's say the child walks to the very center. What should their final angular momentum be?
It's changing its moment of inertia.
We're pretty close to. Yeah, it's changing its moment of inertia. So roughly speaking, child should be 0. Now, by the by, technically it's not, because the child is actually rotating around themselves, man, and we are going to have to use one of those. It's so small relative to what these other moment of inertias are, we're just going to assume that it's 0. So, what does that mean? The merry-go-round has to then do? Speed up. It's going to have more angular momentum than initially did, because you're just adding the child's angular momentum in with the merry-go-rounds, so it should increase, it should speed up. And vice versa, right? If we flip the script and the child walks back out to the outside, what do you expect to happen? The merry-go-round should slow down to where it originally was. Yes? All right. These are relatively simple examples. Relatively not simple, but relative to the examples I'm about to show you. So we got about 5 minutes for a couple of kind of interesting examples. Let's begin with this one. You've got a star. Going around that star is an asteroid. If you didn't know this, most objects going around an object do not make a circle. As a matter of fact, the Earth itself does not make a circle around the sun. Now, just as a heads up to anybody that already knew this, it's so freaking close to being a circle with the Earth, we just go, yeah, it's a circle, it's fine. It's, for most approximations, we are good. Okay? But the actual shape that is made around a star, I'm not going to do a great job, is known as an ellipse. Okay? Because it comes up on the homework, I'm going to share a little bit of information about this. This distance, when you're the closest to the star right here, that guy's known as the perihelion. That's just the distance when you're super close to the star. Okay? And when you are furthest from the star over here is known as the aphelion. Don't spend too much time on those words. They're simply definition words that are like, hey, this is the distance when it's far away, this is the distance when it's close. But here's the interesting thing. This object is moving with a velocity. Very linear thing. You would not usually think about this in the form of rotation. But where is the center point of this particular rotation? Star. Now what that means, when we start to sum the angular momentums, and how many angular momentums are here? Just one. The angular momentum of the asteroid initial, and the angular momentum of the asteroid final. So what does that mean? Well, that means moment of inertia initial times angular velocity initial is equal to moment of inertia final times angular velocity final. Is its moment of inertia changing? Yes. In what way? Let's say it starts here and travels and goes out here. What's moment of inertia doing? So moment of inertia is increasing. So what does that mean has to happen to the angular velocity of the asteroid? Should decrease, which means the asteroid weirdly starts to go slower. Now, to show that, what equation do you use for moment of inertia if it's not at its center? Like if it's not like at rotating around itself, but just somewhere out here, what equation do we use? What's the general equation for moment of inertia if it's not rotating around? If it's rotating around itself, you just go to the table, right? But if it's not rotating around itself, I don't care what the object is, it's out here, what do we use? mr squared. So this would be the mass of the asteroid times the radius squared, this guy right here. And this guy would be mass of asteroid times radius squared. Now notice I put initial and final on radius, but not on mass because there you go. Radius changes, mass doesn't. Do we have an equation that relates angular velocity to linear velocity? What is it? Is equal to angular velocity times r. Therefore, basic algebra says angular velocity is equal to vt over r. Yes? So, this guy is the velocity initial over the radius initial. And this guy is velocity final over radius final. What nice cancellations happen? Close. Be a little bit more specific here.
Well, the radius on the bottom cancels.
One of the radiuses cancel, sure, on both sides. And?
I cancel out the other two in both terms.
Sure, we've done both the radiuses. What else cancels?
Mass.
Mass cancels because it's the same on both sides, leaving us with this interesting equation. That if I double the distance, so if the aphelion somehow doubles the perihelion, what happens to its speed? Cuts in half. It's going to move half as quickly through that particular distance and not cover nearly as much angle in that amount of time. All right, we'll deal with my last complicated example tomorrow in which we relate linear momentum to angular momentum.